What's up? It is 9:51 on Tuesday night. Tuesday night physics problems with Mr. Knight. We'll make it a thing. Sorry for my casual attire, but it's late and I don't feel like being dressed up right now. So you get me at my worst with my hair sticking out and everything. Try and put that back in for you guys. Oh, I made it worse. Okay. So this is 19.1, number 3. First problem to do with solenoids here. This is actually a good one. I like this one. So let's just work through this one together. This will be my last one for tonight because I got to go to bed. Sorry. I always put this thing in this corner, but if I put it here, it makes me feel like I'm talking to you guys. I'll sit up so you can't see that light. So solenoid used to generate a magnetic field, inner radius A, length L, total turns N, power supply not shown, connected to the solenoid, generates current I, blah, blah, blah. X-axis runs along the solenoid, point P is in the middle. Assume L is much greater than A. That just tells us that the solenoid is going to be ideal, right? It's an ideal solenoid because L is much greater than A. We don't have to worry about dysfunction, disformation of the field at the ends or in the middle. So select the correct current or direction of magnetic field at point P. So you can see the direction the current goes. It shows us in the little cutaway view around from the back and then over the top. Obviously, my thumb is pointing to the right in the positive X direction. So there is our answer, positive X direction. Justify our answer, we use the right hand rule. Our fingers curl. With I, which leaves our thumb pointing in the positive X, right? And that's good enough for me, right? Lets us know which direction the field is going in. Cutaway view below, draw an Amperian loop that can be used to determine the magnetic field at point P at the center of the solenoid. So we actually did this in class, if you guys recall, but we'll draw a little rectangle here that has one of its sides at P. And we've got a length for our rectangle. We've got a width for our rectangle. I'm going to call W width. It actually doesn't matter. You will find out what we call that, but I'm going to use W for width. And there's my solenoid. I actually also have to put a direction in which I'm going to integrate. So I'm going to go around counterclockwise here. So when we use Ampere's law, which is it's going to ask us to do, we're going to have to choose a direction for integration. So I'm choosing that now. Use Ampere's law to derive an expression for the magnetic field strength at point P. Express your answer in terms of I, L, N, A, and physical constants. So we're working with Ampere's law, which is the loop integral of B dot dl is equal to mu naught times I enclosed. So let's focus on the left side first here, right? We can actually use this as kind of a sum and add up all of the individual integrals, right? The integral along the bottom, the integral along the top, integral along the two sides, add those all together to get our final answer here. But we can actually simplify it a little bit before we just try and jump ahead and start integrating. First thing to notice, this top part of our Amperian loop is outside of the circle, or it's outside of the solenoid, which means B is 0. If B is 0, that goes away, so we don't have to worry about it. The second thing to notice is part of our side right there is out of the circle. So that's not going to have any effect. Let's talk about the inside. The inside is in a magnetic field that is pointing, like we just answered, from left to right, right in the positive X direction here. And so if you recall, B dot dl is actually B times dl times the cosine of theta, where theta is the angle between B and dl. That's any kind of dot product, right? Dot product always goes to cosine. So cosine is the angle between DL, which is the direction of our integration, and B. And you can see if DL is up here, that's 90 degrees between DL and B. Over here, 90 degrees between DL and B. If the angle is 90 degrees, cosine is 0. So these actually cancel out as well. And we're left with only the bottom. And the bottom is parallel to B. And B is going to be constant at the center. It's going to be uniform at the center of our magnetic field. So B pops out. We get the integral of just DL, which is just the length of this side, right? It's going to be W is equal to mu naught I enclosed. So we get BW equals mu naught I enclosed. All right, and that's kind of where we have to stop for there. W, so far it looks like a bad thing, so we'll have to kind of fix that later if we come to something, because W is not allowed to be in our equation. But let's be over here. Mu is a constant. That's a physical constant is allowed to be in. But I enclosed is not, because it's not the same as I, right? I is the length or the current through one of these loops. We have who knows how many loops in our Amperian loop right here, right? How many turns do we have in there that are contributing to the current? So I enclosed is actually going to be equal to the number of turns that we have enclosed times I, right? The current that's going through each of the turns times the number of turns that we have enclosed. Unfortunately, N enclosed is not allowed to be in there either, because this value N is the total number of turns, and we clearly do not have all of the turns in our Amperian loop there. You actually can't have all of the turns in your loop, or else you start dealing with edge effects, and that's not a good thing. We want to be fully inside our loop here, because if we get out towards this area, we start dealing with varying magnetic fields because of edge effects, and B doesn't pull out of our integral, and that becomes very difficult. So we have to figure out a way to deal with this N enclosed. How do we figure out how many turns do we have enclosed? And we're kind of going to second-handly use turn density, right? Turn density lowercase n, which we've used a lot, but turn density is the total amount of turns divided by the length of the solenoid, right? That gives us turns per length, right? Turns per length. So if we know the turns per length, and we multiply by the amount of length that we have, which is W, right? This made up variable W, we can actually get the number of turns. So it's like a second-hand way of getting to the number of turns enclosed. Number of turns enclosed is going to be this times W, right? Turn density times the length that we're using. So the I enclosed is going to be equal to N over L times W times I. N is good. That's the N that we're allowed to use. L is good. That's the L that we're allowed to use. W is still not good because we're not allowed to use it, but I is good. So we've gotten a lot closer. So let's plug that in. BW equals mu naught N W I over L. And lucky us, we get a W on both sides in the numerator. It cancels, and we get B is equal to mu naught N I over L, the equation for a solenoid. That's what we got. So that one's not too bad. Not too bad, not too bad. A lot of the stuff canceled there, which makes it nice for us. All right. I have this one. I set some of this up already, so that didn't take me forever to do it. But some physics students conducted an experiment to determine the resistance of a solenoid with a radius A equals 0.15, 100 turns, length of 0.4. Connect the solenoid to a variable power source. Measure the field along the central axis of the solenoid at point P. Plot of the magnetic field strength as a function of EMF is shown below. So we have magnetic field versus EMF. I just calculated, I have my calculation for slope here, and eventually my calculation for resistance, which is what it has to draw. But on the graph above, draw a best fit line. So I did that. There's my black best fit line. I picked 2 points on it because the next part is determine the resistance. So let's figure out how I got this equation to solve for R, right? Because that might not be super apparent. The only equation we have to work with right now is magnetic field is mu naught times N times I over L, right? Which doesn't seem like it's that great for us because it doesn't have E in it, right? It doesn't have potential in it. It doesn't have EMF. All it has is I. But we have Ohm's law, which tells us that I is equal to V divided by R. V is essentially the same thing as E. So that's not multiplication. I'm just telling you that they're essentially the same thing. So we can replace I with E over R. So we can get magnetic field is equal to mu naught N E over LR. And then we have an equation that has B in the y-axis spot if we were to y equals mx, right? And it's got E in an x spot, which means everything that's left over is the slope of the line. So if we're able to find the slope of the line, we can set it equal to mu naught N over LR, and we can solve. So that's what I did over here. I found the slope. I used the point 0, 0, and 1, 2.5, right? 2.5, 3, 3.54. Yeah, 2.5. So rise over run, divide. We get 4 times 10 to the negative fifth. We plug that in, and then mu is 4 pi times 10 to the negative seventh, and it gives us as 100. You can find mu in the table of, in the constants in the equation sheet. L it gave us as 0.4. We solve all that. I got my resistance as 7.9 ohms. I think in the answer sheet, they get something that's a little bit higher than that. Do I have it open here? That's the end of the problem. Oh, too far. Yeah, they get 8.7. So they got something that was a little bit higher than, a little bit steeper than what I had. So not sure why. Who knows? We obviously picked different points for our slope. So they got a different slope than I did. They got a much shallower slope, or much steeper slope. What did I get? I forget what I even got. I got 4 times 10 to the negative fifth. They got 3 times 10 to the 3.6 times 10 to the negative. So they got a smaller slope than I got. So that's fine, right? It works out. Same difference. Close enough. So I got 7.9 ohms as my resistance of the solenoid. One of the students notes that the horizontal cone of magnetic field is 2.5 times 10 to the negative fifth Tesla. Is there evidence from the graph that suggests that the horizontal orientation of the solenoid affects the measured values for B? So basically what they're saying is, well, we have our solenoid going sideways here, right? And we know that the Earth's magnetic field points sideways. So if our magnetic field that we're measuring is being created this way, right, is the Earth's magnetic field, which is everywhere, right, affecting our measured value for the magnetic field inside? It could either be too high because the Earth's magnetic field is pointing parallel with it, or it could be too low because the magnetic field, Earth's magnetic field is pointing away from it, right? So is that having an effect? And the answer is you could have either yes or no for this one, right? There are actually 2 answers. Either one could be justifiably correct. Mine is no. Why is mine no? Mine is no because when the EMF is 0, right, when there's no current through our circuit, my magnetic field is 0, which means when my magnetic field is just sitting here, right, plain, there's no Earth's magnetic field that we're accidentally measuring at the center of my solenoid, right? It's 0. If the Earth's magnetic field was having an effect, I would either get a measured value of 2.5 times 10 to the negative fifth Tesla, or some other number, right? It doesn't have to be perfectly aligned, but the magnetic, or the y-intercept would not be perfectly 0 if the Earth's magnetic field was having an impact. So my answer is no. because my y-intercept is 0, right? Essentially, when E is 0, B is 0, right? That's my justification for that. When I have no EMF, I have no magnetic field, right? If we had magnetic field being measured at the center when there was no EMF, then we could have that playing in a role. Would the horizontal orientation of the solenoid affect the calculated value for R? That one's always going to be no. Regardless of whether Earth's magnetic field is affecting our problem or not, the answer is going to be no, because what we're looking at when we're calculating R, right, is the change in magnetic field with respect to the change in EMF. So R is calculated based on change in magnetic field and change in EMF. The fact that we have 2.5 times 10 to the negative fifth added everywhere, or 2.5 times 10 to the negative fifth subtracted everywhere, isn't going to affect the change, right? The change will be the same regardless if we have a higher y-intercept or a lower y-intercept, right? Because we're calculating R based on the changes, the Earth's magnetic field is never going to play a role. This was a long one. All right, thin conducting loop of radius B, resistance RL, placed concentric with a solenoid as shown above. Current in the solenoid is decreasing from I to 0. So our current is decreasing. Is the direction of current induced in the loop clockwise or counterclockwise during the time period? So let's look at our magnetic field originally, right? Our original magnetic field, which we stated already, goes to the right in the positive x direction. If our current is decreasing, right, that's going to mean that the magnetic field in our solenoid is going to decrease as well, which means it's going to go from this long magnetic arrow to a much smaller magnetic field arrow. Our induced magnetic field, our induced current, is going to act to oppose that, right? It wants to keep the magnetic field the same. So our magnetic field was big, it's getting smaller. Our current's going to try and create more magnetic field to make up for that difference, right? It's going to try and create magnetic field this way to keep it what it was, right? It wants everything to stay the same. So in order to create magnetic field that way, to support our decreasing magnetic field, we would need our current to go clockwise. Right, and justify, we just did. Current B in the positive x direction is decreasing. Right, magnetic field B induced will oppose that change. Which means it's going to be induced in the positive x direction. In order to have magnetic field induced in the positive x direction, current needs to go clockwise by the right-hand rule. Right? In order to create field that goes to the positive x to support the magnetic field that's decreasing in the positive x, our right-hand rule tells us that we need to go clockwise there. Derive an equation for the average induced current in the loop during the time period that the current in the solenoid is decreasing. Express your answer in terms of I, L, N, A, B, R, L, R, S, T, and physical constants as appropriate, which means we don't need to use all of them, but that's what we have available to use. So EMF is equal to change in flux over change in area. What's that? That's Faraday's law, right? So Faraday's law tells us change in flux over change in area. I think, did I get that right? Faraday's law, EMF right here, change in flux over change in time. All right, good. I messed it up. See, there we go. That's why we have equation sheets. Sorry, it's 10:11. It's 11 minutes past my bedtime. So flux in a uniform magnetic field, which if we take snapshots of time, our magnetic field is uniform here. Oh, excuse me. So we're going to get EMF equals dB times A, right? If our B field is uniform, we get B times A over dt. Area is staying the same, so it's actually magnetic field that's changing. So we get EMF equals A, area stays constant, change in magnetic field over change in time. Okay, so our magnetic field is changing with time, all good. But there's some stuff that we can't use, right? We can't use A is no good. We can't use delta B is no good. We can't use E is no good. So we have some things to replace. So EMF in our loop, right? If we use Ohm's law, EMF is equal to I times R, where I is the induced current, right, in the loop, and R is the resistance of the loop. So we get I induced times resistance in the loop is equal to A times delta B over delta T. Okay, A we can replace, right? A is the area through which the flux is passing. All right, that we need to be careful with that because A is not the area of the big loop. A is the area in which the flux is changing, and the flux is changing in the smaller loop inside the solenoid. So that's actually going to be 2 pi, or not 2, pi A squared. So our area, we have I induced is equal to, we're looking for I induced, right? Okay, so I'll keep I induced by itself. I'm going to move RL over to the other side, but A is going to be pi A squared over RL times delta T. We're getting closer. We still need to get rid of delta B. B in a solenoid, we have an equation for. We used it a couple times already, right? B is equal to mu naught Ni over L. L we can use, N we can use, I we can use. There we go, right? So we substitute that in. Mu is a physical constant, so that's fine. And we get our induced current is going to be equal to pi A squared mu naught N I over delta T. And there we go. If you look at the answer key, and this is one thing I'm not 100% sure about, the delta for the I, they just kind of drop it off. And I'm not sure how or why they were able to drop it off, but they just kind of get rid of it. They like, we don't really want that delta anymore. I'm not 100% sure why that delta is able to disappear. Because the current is still changing. But I guess if we look at a certain point in time, right, if we just look at, I don't know. I don't know how they get rid of the delta there. Right? If we look at the solution guide, past that. Past that. All right, we set it up. We got that. We substitute in the correct A, right? And here they have delta IL over RLT. And then in the next one, right, they set it equal to, and nothing changes except for the L goes to the bottom, which I'm fine with, right? That makes sense. But the delta disappears from the I. So I don't know if that's a on purpose or accidental, or if there's a reason that the I doesn't need a delta anymore. But I'm not 100% sure about that one. I forgot the L actually, right? The L drops to the bottom. I forgot the RL too. RL, this comes with an L with it. So RL is still in the bottom and L drops down there too. So we end up with our I enclosed is equal to pi A squared mu naught Ni over RL delta T L. as our equation for the enclosed or induced current. And that is where I am stopping for tonight. It's my bedtime. How do I stop this? This is embarrassing. Now it's even more embarrassing because my face is bigger.